Hello, this is Stuart Mason with Math 156 Script 1B, and we're going to be doing a slightly more complicated probability data frame problem. So we're going to be dealing with a deck of cards, and the first thing we need to do is create a data frame that represents one row for each possible card. So we'll tell R about the suits, and we'll tell it about the ranks, ace through king, and we'll use expand.grid to generate the Cartesian product that has all possible outcomes. And the result is this nice long list, 52 elements long, of each possible suit and rank combination. Then we name the columns and convert the result to a data frame. We can create a contingency table of the data frame. So what this tells us is the value of the suit and the value of the rank and how many times each of those occur. And as you can see, each suit rank combination occurs only once, which makes sense if we're playing with a fair deck. Finally, we can write this to a comma-separated value file in order to save it for later use. When you do this, keep in mind that your working directory matters, which we talked about a little in class on Wednesday, and also there's some information about directories on the course website. I recommend generating a Math 156 folder where all these things can live. So let's see where I'm working currently. Get working directory, my home directory. So I'm just going to go set working directory, tilde, desktop, Math 156. Now if I take get WD again, we see that's where I am now. This only works because I created it there, so make sure that you create a Math 156 folder somewhere and learn the path to it, and then you can set it. You can also use the Files tab, and if you come over here to this triple dot, it'll bring up a browser that you can use to navigate around and find the folder you want. Then you type more and hit set as working directory, and then your current folder will be set by R to the folder you just selected. So after we write this, suppose we then did something else, we worked on another problem, we closed R, and then we open it again and we want our deck of cards back. We can read.csv, provided we're looking in the right place. By looking in the right place, I mean in the right directory. And then if we reload it and tabulate it, you see we get back what we asked for, although Paul points out that information is lost when it's saved in a CSV file. In this case, it looks like R took the ranks, and instead of reporting them in the order we told R about them, it reported them in alphabetical order. And that's got to do with the fact that R understands these to be something more complicated than strings. It understands them as factors, and factors have a level where the order matters. So we'd have to refactor them with the appropriate levels. And I talked about this a little bit on Wednesday, when I showed how to make the days of the week show up in order instead of in alphabetical order. And if you have questions about that, feel free to reach out to me. Okay, so now we want to draw two cards with replacement. So it's essentially we're taking two decks and stacking them on top of each other. And the result is a very large Cartesian product, 52 by 52. Right? And in fact, let's name it. We look at the head, and you see it's got the ace of clubs from the second deck matched with all possible aces from the first deck. And so this can be thought of, basically you have all combinations of drawing a card from a deck twice. And if we look at the number of rows, it's quite big. And in fact, it's the same thing as 52 squared because there's 52 options twice. In order to simulate drawing two cards without replacement, so think of this like dealing two cards, we need to take out the duplicates. And so we're going to use the subset function to do that. Subset takes as its first argument a data frame that you would like to pare down, and the second argument is a logical statement. All the rows that satisfy this statement will be kept in the subset. So there's a couple things going on here. I'm first going to talk about this bar. So this is R's OR operator, which means that it will return true if the expression on the left is true, or the expression on the right is true, or if they're both true. So suit 1 is not the same thing as suit 2, or rank 1 is not the same thing as rank 2. And obviously, if either of these conditions is satisfied, then we know that the cards are not the same, and so that's a sufficient logical condition to move all the pairs. If we take a look at the head, again, it looks very familiar, except now there is no ace of clubs corresponding to the ace of clubs set, because we took out that set where they are both the same. And if we count up the number of rows, there are a few missing, right? 52 missing because all the pairs have been removed. And we can turn this to a data frame and save it. This dim function just tells us its dimensions as a vector. So we get 2,652 rows and 4 columns. And looks like Paul reads it back into memory and talks about some of the wonkiness that happens. So because we saved it with row names, we get this kind of extra X column, which tries to keep the row names. If you want to make that not happen, just read up on how read.csv works using the help file. And you can see there's information here, for example, about you can warn for loss, you can row names is a argument that you can use to not have it write the row names. Then when you read it back in, you won't get this X column. So now let's do some probability. First, we're going to check what's the probability that the first card is a spade. And we're going to do that by extracting the suit from the first card, which uses this $ operator. The result is this very long vector of different possible suit outcomes. Then we're going to use this double equals sign to check equality. Remember, double equals checks equality, single equals assigns equality. And we say, okay, CP suit 1, is it equal to spades? And the result is a long logical vector of falses and trues, which has a true for every element where the element of CP suit 1 is a spade. Now R is smart enough to understand that when we call a numeric function on a logical vector, the falses are zeros and the trues are ones. So if we take the mean of this vector, we're basically averaging out a bunch of zeros and ones. In other words, we're summing up all the ones where spade is true and dividing this by all the possible cards, which is the count of all the values. And the result of that is a quarter, which intuitively matches the theoretical probability of drawing a spade. The same is true for the second card. Of course, it gets a little more complicated if we talk about drawing two spades. Now we need another logical operator, R's AND operator. So we're saying take the mean of the logical vector where suit 1 is a spade and suit 2 is a spade. And the result of that equals the probability that we could calculate using the sort of independent expectation. And then the probability of drawing at least one spade, we again use this OR operator, right? So CP suit 1 is spade or CP suit 2 is spade. And this is also going to match the theoretical calculation of 15/34. If you're curious about where these numbers are coming from, reach out to me and I'll walk you through the algebra. Now the inclusion-exclusion rule, I think of this like a Venn diagram. So basically the probability that A or B happens is the same as the sum of them happening minus the probability that they both happen. And the reason for that is when you sum the probabilities of either of them happening, the probability that they both happen gets counted twice. And there's a very pleasing Venn diagram expression of this if you'd like to see it. But so we're just going to say, is probability A or B, remember we're checking equality, is probability A or B equal to that expression? And R will say that you didn't run all the expressions, Stuart. Let's go through and do that again. And R will say, yes, in fact it is true. All right, what's the probability that they're the same suit? Well, that's just going to be CP suit 1 double equals C2. And sure enough, that equals the theoretic probability of 4/17. Now we've used R to answer all kinds of probabilistic questions. Let's do some statistics. Remember before we used the sample function to grab random indices from a data frame? So now we're going to do that again. If we say that row is going to be some sample from 1 to n rows of the card pairs, we only want one of them, and row turns out to be 548, and that's what row 548 looks like. Now we can count the number of spades by asking, does suit 1 equal spades and does suit 2 equal spades, and add them together. So this can either be 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. And we can see by inspecting the situation that we actually drew 2 hearts, so this should be 0, as it is. But now that we have an idea that this operation works, we can do it any number of times we want. So in this case, Paul says 10,000. And we're going to initialize a vector that is going to be type numeric for storing the number of spades we get. And we're going to initialize a logical vector for counting if they were the same suit or not. And now here we have a fairly complicated for loop. So just to touch on this, because this is not a computing course, we're going to say for the value I in all possible values between 1 and n, which we said to be 10,000, we would like to get one row from the data frame, and then we'll do this operation to see how many spades there are and store that in the ith position of the n spades vector, and we'll check if they're the same suit and store that in the ith position of the same suit vector. And so R is going to think for a minute and do that for us, and we can tabulate the result, and you see most of the time we got no spades, occasionally we got 1 spade, and very rarely we got 2. And then we can check to see if these results match the theoretical probabilities. So how often did we get 2 spades, and what's the probability of A and B being a spade? Close, but not quite the same because of the variance. What's the probability of getting at least one spade? Again, close but not the same. And what's the probability that they were the same suit? Close but not the same. Of course, we don't need 2 decks to do this, right? We can just call back to memory our original deck, and we can just sample from cards 1 through 52, asking for 2. And I think by default, replacement is false. Let's check the help function to verify that. So I come over here and I say yes, replace is specified to be false by default. So in other words, sampling 2 values from our deck, we're guaranteed they're not going to be the same. And now these, of course, are just indices, right? We'd have to go to deck 33, 44 to see exactly what the sample was. The problem there that I got the error was I forgot to include this comma, so it didn't know which columns I wanted. By telling it comma space nothing, it says, oh, he wants all columns. So we can do this again, repeating this logic and just doing using one deck, and we're going to get a very similar result, right? So 0 is about twice as common as 1, 2 is very rare, and of course the actual observed statistics are not quite the same as the expected probabilities, but they're very close. Great, hope that was helpful. Again, feel free to reach out to smason@post.harvard.edu with questions, and I'll see you guys on Wednesday.